I have to start a new chapter. Chapter 4 on metals. Now, we did metals in grade 8 for the first time. What are the differences in properties between metals and non-metals? Just shortly. Metals are shiny, malleable, ductile, sonorous, good conductors of heat, good conductors of electricity. Okay, now we are starting out very simply. The chemical properties of metals depend on the arrangement of electrons in the metal atoms. It's basically got to do with how it is bonded. All right. Remember, chemical properties involve making and breaking of chemical bonds. So chemical properties would be properties the substance has due to the bonding between the particles. Now, the physical properties simply on how the atoms are arranged together in the metal crystal. Now, metallic bond, we've done that in grade 10. Who can remember? Yeah. Crystal lattice implies there's an orderly arrangement of particles. These particles are charged. Yes, we say the orderly arrangement of positive atomic rests, and they are positive, so where are the negatives? The outer shell electrons, they become delocalized. What does delocalized mean? They can move from one atom to another. It's as if they don't stick to the atom that it should be with. Okay, so here I just have two examples. Zinc, the positive atomic rest has a charge of +2. So each zinc ion is responsible for giving off 2 electrons that can travel through the metal. Sodium has a charge of +1. There's only one outer shell electron, so each sodium atom is responsible for giving off 1 electron or allowing 1 electron to be delocalized. Yes, probably. Okay. The properties of metals, we've just done them: shiny, malleable, ductile, sonorous, good conductors of heat, good conductors of electricity. And then we go and add, usually, metals have high melting and boiling points. What are the exceptions? Group 1 and 2 metals. And usually they have high densities. What are the exceptions? Group 1 and 2. Okay. So, if we have to explain the physical properties of metals, why are they shiny? Why are they malleable? Why are they ductile? It all goes back basically to the delocalized electrons and the fact that the positive atomic rests are packed in layers in an orderly arrangement, a repeating pattern. So, why do metals have high boiling points? What forces hold these particles together? Why don't the positive atomic rests jump apart? There are delocalized electrons that hold them together. It is an electrostatic force. Coulomb forces are fairly strong. Yeah. So, atoms are held together by strong Coulomb forces. If those forces are strong, we require a lot of energy to separate the nuclei from each other, or the ions from each other. Why do metals have high densities? Same reason. Forces holding particles together are strong. If you have stronger forces pulling particles in closer, it'll be more dense. So, forces holding the particles together are strong, therefore the particles are arranged close together. Why can they conduct electricity? Now, yes, but why does the outer shell electron become delocalized? We say that metals have low ionization energies. Now, ionization is the energy involved in removing an electron from the outer shell, taking it away to infinity. So if metals have low ionization energies, they don't have a strong attractive force on the outer shell electrons. Do you follow? So, metals have low ionization energies. Therefore, the outer shell electrons are delocalized. It's easy to remove them because the force holding them in the outer shell is not strong. And they can travel through the metal. Electrons will travel away from the negative terminal if you put a potential difference across a metal, and it will travel towards the positive terminal. Why? Yes, opposite attract, like charges repel. Conductivity of metals. Why are metals good conductors? Yes, they have delocalized electrons that can travel through the metal. Now, in terms of heat conductivity, there are two ways in which heat can be, or three ways in which heat can be transferred. The one is by conduction. What does the definition, the word conduction mean? Energy bumps or particles vibrate, they bump into each other and it transfers the energy by direct contact. So the positive atomic rests, they gain energy, they start vibrating and they can bump into each other, transferring the energy by direct contact. The other thing is that the electrons are delocalized and they can also pick up energy and move more. All right. Delocalized electrons can carry the energy through the metal. Yes. They aren't stuck around in the outer shell. They are removed from the outer shell. Okay. So these delocalized electrons also play a role. They also go bumping into the positive atomic rests, and that also transfers energy. Okay. So both heat conductivity and electrical conductivity, due to the delocalized electrons that can move, the heat conduction is very good in metals because the positive atomic rests can vibrate and transfer the energy by conduction, direct contact, and the electrons can also move and carry the energy. The next property, malleability and ductile, they go together. The collective word for this is they are workable. All right? Meaning you can hit it with a hammer, it won't shatter, but you'll hit a dent into it, it'll change shape. And you can pull metals into threads. We call those threads wires. All right. Now, why can this be done? Well, very simply, these positive atomic rests are arranged in layers, orderly arrangement of particles. And between the positive atomic rests, in terms of layers, there are delocalized electrons. So in its simplest form, if I start pulling on a metal, I can stretch, not really stretch it, but I can make it longer if I pull a piece of metal. The reason why is these positive atomic rests can slide off each other without breaking apart because the delocalized electrons maintain the attractive force between the separate layers. Okay, and within a layer as well. So that is ductile. Why malleable? Just very simply, if you hit it with a hammer, you force positive atomic rests out of their orderly arrangement. But it doesn't matter because there are negative delocalized electrons that still hold them together. Okay, so bonds holding the atoms together in the crystal lattice are strong but not rigid. And they aren't rigid because of the delocalized electrons. The sea of electrons keep the layers together, allows the positive atomic rests to slide off each other. That's the end there. Now, from the work you've done in grade 9 at some other point, we did the reactivity of metals. Grade 10. Some metals are more reactive than others. How could I prove that to you? Yes. Take a block of sodium, put it on the desk, leave it there for a while. What's going to happen? It's going to start burning. Okay? Take a piece of steel, put it outside in the rain. After a while, it's going to rust. Okay. What about gold? When ships sink carrying gold coins, do those gold coins rust away in the oceans? No. Hundreds of years later, they can be dived up from the seabed. They have not reacted with the water or the oxygen or any of the salts present in the water. Why that? They are unreactive. All right, so we can set up a reactivity series. Some metals are definitely more reactive, okay, than others. In terms of being more reactive, what does it mean? It actually means that they have a greater tendency to form ions. How do metals form ions? They lose their outer shell electrons. In other words, it comes down to metals have low ionization energies. But within that concept, some metals have lower ionization energies than others. Those with the lowest would be the most reactive because they easily give off their outer shell electrons. The less reactive ones tend to hold on to their outer shell electrons more than the more reactive ones. So we can set up a reactivity series. You know the group 1 metals are more reactive as we go down the group. Similarly, the group 2 metals also. Now, it can be more complicated than this, but your syllabus simply refers to, I think, a little bit on the reactive range, a little bit on the less reactive range, and a little bit on the least or unreactive range. So for your purposes, you must know potassium is the most reactive. Okay? Very reactive. Sodium, similarly, even more actually than potassium. Now, no, potassium is sodium, potassium. Potassium is more reactive than sodium. Yeah, I've got it there. I thought I had it the other way around. So potassium, very reactive, then sodium. And as we go down the board, I can, for example, store a piece of calcium in a bottle or on the shelf, and it won't necessarily start burning. But after a couple of weeks, a white heap of powder will be left. Calcium oxide would have formed. Yes, it's oxidized. Magnesium is also very reactive. I can take a Bunsen burner and I can hold it in the flame and the magnesium will start burning. Zinc, less reactive than magnesium. Iron, less than zinc. Lead, becoming unreactive. Copper, less. Silver, gold, and platinum. Oh, unreactive. Why do they make jewelry from silver, gold, and platinum? They remain shiny. You with me? No? Yeah. So these elements are unreactive. They don't want to react. It's not that it's impossible for them to react. How is the gold mined at B2 Gold? In what form? Pure little lumps of gold? No. That they do in Alaska in the cold water? No, not solid gold. It's mined as an ore, which is a compound containing gold. All right. Yeah. So it's not impossible for these metals to react. It's just they don't really like to react. All right. If you look at them, if we heat the metals, the more reactive ones will burn with a flame. Sodium and potassium. Sodium has, if I remember correctly, a yellowish flame, and potassium has a purple flame. This color purple. Yes, if I put them in a flame. Or, well, sometimes potassium and sodium, I can just leave. But, yes, and you heat it up, it's going to go even better. Then the elements, zinc and iron, and then from there, they don't burn. I can heat them up, they won't burn. These cars that started spontaneously burning. You know what I'm talking about? What was the problem? Yes, they reckon, if I've got the story correctly, somewhere in the gearbox they use an alloy containing lots of magnesium because it's light and it's strong. And then apparently one of the seals tend to break easily and it doesn't insulate the gearbox part from the heat. And at a certain point, if you've been driving long enough, there's a lot of heat generated, and if you've got enough heat, it starts burning. And you cannot easily put out a magnesium flame. It burns very violently. And that is why, even if they try pouring water on it or using a fire extinguisher, you usually don't have enough to put out the flame. Magnesium burns with a very bright white flame. Yeah, yeah. Okay, that's why they use it in flares. They add magnesium to the flare, makes the very bright white light. Okay. Um, the metals then from zinc down to platinum, gold, copper, silver, those, they do not burn. Okay, but they do eventually react with the air to form an oxide, so the surface will become dull. That is why if you have got copper ornaments at home, so after a long period of time they become dull and you need to polish them up. When you polish them, you remove that oxide layer. So this is usually those metals. The zinc oxide that forms on the layer, zinc oxide has a whitish color. Iron oxide, a reddish brown. Lead oxide, I think, is also white. And copper oxide, blue-green color. All right. If we're going to have a look at the reaction of these metals with steam in comparison to the reaction of metals with cold water, we find that sodium, potassium, calcium, magnesium, zinc, iron react fairly easily with steam. Okay, and the products that are formed are hydrogen. Okay, lead and copper tend not to react with steam. Sometimes you can encourage copper to react by heating it fairly high. If you have two flames, you can heat up the copper, and if you've got finely divided copper and you've got some water trapped in a test tube and you heat it and it starts boiling and the whole system is hot enough, the water doesn't condense. If the steam then makes contact with a very hot copper, it sometimes tends to form copper oxide plus hydrogen. Reactions of the metals with acids. When a metal reacts with an acid, products are salt and hydrogen. So, sodium, potassium, and calcium, people, they react violently with water. I will not add them to an acid. They will be those reactions will be very, very violent. The reaction is also exothermic, so the metals tend to melt. They have low melting and boiling points, so they form a liquid. And they react violently with the water, so it can cause them to splutter and splash. And if some of that hot, burning metal lands on you, you can't add water to kill it. All right? Yeah, it will burn a hole in your flesh. So we don't add these metals to acids, but if you would, you will have an extremely violent reaction. Product will also be a salt and hydrogen gas. By the way, how do we test for hydrogen? Burning splint makes a blue flame, popping or whistling sound. Magnesium, zinc, and iron, they react fairly decently with an acid fairly controlled in a container. It will bubble, the container will become hot. It will form the salt plus hydrogen. For example, if I add zinc to hydrochloric acid, what salt will I get? Zinc chloride plus hydrogen gas. All right. If they ask you include state symbols, then you have to do it. Yeah? Magnesium. Yes. Because it's slightly more reactive than the others. Okay. Oh, you can also go and look at the balancing of the equation. If you have zinc chloride, you will need 2 there. So that one will give you, for every 2 molecules of acid, you'll get 1 molecule of hydrogen. If we looked at something like, let's take aluminium. Okay, aluminium messes a person around, but if you could get it to react, if we made it react with HCl, it will require some encouragement, but we will get aluminium chloride plus how many hydrogens? So we would not have 3 there, we would have 6 there. So we would get 3 hydrogen molecules. Okay. No, not too bad. Okay. Let's do one new thing. Yeah. In grade 8, 9, 10, somewhere along the line, you did the concept of galvanizing. Who can remember what galvanizing is? Covering a more reactive metal with a, no, covering a less reactive metal with a more reactive one. Zinc coating or gold plating or whatever. Okay. The galvanized iron sheets on the roof, they've been galvanized. It's iron dipped in zinc. The zinc is more reactive than the iron. Zinc is more reactive than iron. All right? And the zinc prevents the iron from rusting. Why? How does it do that? We find because their reactivities differ, these two metals fight over electrons. The more reactive one tends to give its electrons away. So, what is going to happen is if I have, let's just leave those for a moment. If we go and look at galvanizing, I have got iron sheets covered with zinc metal. These two fight over electrons. The zinc is more reactive, so it will give off its electron. But look what happens. If iron would rust, let's say I drilled a hole through it and it wants to rust over there, we will get iron oxide, Fe2O3. The moment iron oxide comes into contact with zinc, now the whole metal is covered with it. Do corrugated iron sheets rust there where you drill a hole? Nope, they don't rust. Why don't they rust? Because the zinc competes with the iron ions. This is iron 3+. They fight with each other. The iron wants to get electrons. The zinc is more reactive than the iron, so we get zinc oxide plus iron. So the iron, even though it would start rusting, there's a chemical reaction that pushes it back, that prevents it from forming the iron oxide, because the moment it starts forming, the zinc displaces the iron and it forms zinc oxide and iron. Another property of the zinc oxide is that it is fairly insoluble in water. Iron oxide is very soluble in water. So if I have a piece of steel that's rusting, if it rains, it washes off that layer and the next layer of iron is exposed and it can rust. The zinc tends not to be water soluble. It is slightly water soluble, but not as soluble as iron oxide. So the zinc oxide forms a layer on the metal sheet. Some corrugated iron roofs, they aren't shiny anymore. Why aren't they shiny? There's some zinc oxide on it. So it's no longer shiny. Now this displacement reaction is commonly known as the thermit process there, or we refer to it as sacrificial metal protection. Another good example that they do is out in the Walfish Bay Harbour, the ships are made from which metal? Steel, iron. What happens to steel and iron? Because the ships aren't completely painted. Okay? They rust. So what do? They fix strips of magnesium onto the hull on the outside. Magnesium is more reactive than iron. So the moment I have iron oxide and we have somewhere along the metal part the magnesium in contact with the iron, the electrons can be transferred. They're both conductors. They fight over electrons, and magnesium is more reactive than iron, so we will get the formation of magnesium oxide and iron. So the iron doesn't want to rust. Why can't we use magnesium on motor cars? Because of the heat. It is eventually going to start burning. Why can they use it on ships? There's water on the outside. If it starts burning, so what? It's surrounded by water. Do you understand? Okay, so I'm going to stop at this point. There are 4 equations now, especially for you. See which ones will react and which ones won't. When won't it react? For example, this reaction, copper is less reactive than zinc. So the copper cannot displace the zinc. So there's going to be no reaction. So the first one is done. You can figure out the last 3.